How do you measure the quantum connection between two fields that exist in the same location but differ only by internal properties like color? Traditional geometric tools fail to capture these internal links, leaving a gap in our understanding of quantum gravity. This paper introduces a method called path integral surgery to solve this problem, or introduced to the situation world. The standard replica trick is the workhorse for calculating entanglement entropy, but it relies on a purely geometric intuition, gluing copies of space together. This works perfectly when you are physically partitioning a region, but it breaks down completely when you try to entangle internal degrees of freedom, such as the color charge in a gauge theory. Overcoming this limitation is vital for holography, especially for systems that lack a traditional spatial boundary, like D0 branes. To understand how entanglement relates to geometry in internal spaces, such as the sphere in ADS cross S5, we need a tool that goes beyond simple spatial cuts. The authors propose a novel technique called path integral surgery. Instead of modifying the underlying manifold, they effectively cut and glue the path integral using correlated averages over specific operator insertions. This creates what they call generalized replica manifolds. The mechanism relies on two complementary operations. To perform a cut, the researchers insert operators coupled to momentum, which act like projections that break correlations in Euclidean time. To glue segments back together, they insert position-coupled sources that identify fields across different boundaries. To prove this works, the paper demonstrates the method on a single harmonic oscillator. By applying precise kicks to position and momentum in phase space, they successfully recover the expected partition functions, validating that these averages mimic geometric gluing. When extended to local field theories, this surgery introduces auxiliary defect fields living on surfaces one dimension lower than the bulk. These defects are not just mathematical artifacts, they form a coherent theory that inherits the gauge structure of the original system. A striking result emerges when applying this to matrix models. The authors show that entangling color degrees of freedom in a gauge-invariant way transforms the effective description into a quiver gauge theory structure, revealing hidden order within the internal space. This method bridges a gap in the holographic dictionary. It suggests that internal entanglement in the CFT corresponds to specific bulk geometric configurations in gravity, potentially offering a concrete way to describe Euclidean wormholes connecting internal spaces. The approach is currently specific to a certain class of operations. The surgery relies on insertions that form representations of the Heisenberg group, meaning the method depends heavily on using phase space displacements to construct the cuts. Finally, the researchers explored the large N limit using vector models. They found that the surgery significantly modifies the gap equation, indicating that partitioning internal degrees of freedom causes a back reaction on the semi-classical physics of the system. To learn more, head to emergentmind.com.